Let's talk about limits to performance, limits to endurance performance. So this is part 3 of chapter 3 of the law of running. Questions that come to mind when I go through material in this chapter is, why do people stop at the end of a maximal effort graded exercise test? What is that? What causes that? Why do athletes collapse at the end of an Ironman or the end of a marathon? What limits the ability to cover endurance distance in the shortest period of time? How does a runner get under 2 hours for the marathon? How do you minimize the influence of fatigue, more of a general term, or how do you prevent fatigue? These are questions that come to mind as I start reading this section of the textbook, and questions that we don't have the answers to, but hopefully as we start going through this material, you can start thinking this way and thinking about what the answers may be. So Noakes does introduce, again, this idea of central governor model, and he uses this study and these data to illustrate the point that central governor model is probably a factor here in limits to performance. On the y-axis is normalized data. What these data are electromyography data. Electromyography data are just electrical activity of muscles. We know that for a muscle to contract, the central nervous system needs to send a signal to the muscles. That signal is an electrical signal. We can put sensors on the body or even in the muscle to detect that electrical activity. And we interpret that electrical activity as being muscle activity. So the more electrical activity, the greater activity the muscle is seeing. There's some limitations to that, and as you learn about EMG, electromyography, you learn the limitations of it. EMG is a very similar concept to EKG or ECG, electrocardiograph. That's electrical activity of the heart, or EEG, electroencephalogram. That's the electrical activity of the brain. So same concept, just electrical activity of the muscle. So in this study, what they have are two data points presented for a group of subjects. And what they did is they had these subjects exercise for 60 minutes. And at every interval here, the subjects went all out. Okay, they did a 1-minute sprint. And during that 1-minute sprint, they measured power output. Okay, that's a very typical measurement for cycle types, and this is cycling, a cycle type of study, because we can measure mechanical power at the wheel. And that gives us a sense of how intense the exercise is. And then they also measured EMG. What they noticed was during this 60-minute all-out cycle test, the amount of power generated at each interval here decreased up until the end. And electroactivity followed that same pattern. Decreased electroactivity until the end, and then some increase. Noakes uses data like these to illustrate the point that there's probably something going on with the brain managing the amount of muscle activity during exercise. So clearly, the subjects at the end were able to generate more power. That doesn't make sense if they're trying to go all out for 60 minutes. But in that last minute, they were able to give that surge. And we see that a lot in endurance exercise. That sprint for the finish at the end of a marathon, the end of an Ironman, that last bit, you're able to just draw your effort together and really go all out and cross that line. So why not just this continued decrease in power output? Something's going on here. And same thing here. As muscle activity is going down, power output's going down. So maybe what's happening is the brain is telling muscles to fire less for some reason, but then at the end, the brain says, okay, go for it. We'll recruit more muscle, have greater muscle activity, and generate more muscle power. So the idea behind the central governor model is there's something that the brain is doing to regulate how active muscles are during the course of exercise. All right, so keep that in mind. That's a good model that we're going to have to talk about. That really pulls in all different areas of kinesiology to try to understand. The other way to think about limits to performance is an energy supply model. So it's just a little different. This is stating that performance, endurance performance, is limited by the availability of substrate, fuel, and capacity of the metabolic pathways, the anaerobic pathway and the aerobic pathway, that these are tapped out and that you can't go any further because either you don't have fuel or your energy pathways can't convert that fuel or transform that fuel from the chemical state to mechanical state. And therefore, superior endurance performance is a function of being able to produce ATP aerobically, specifically, and probably anaerobically as well. Fatigue would result by the breakdown of the metabolic pathway, that is the lack of available substrate or lack of available something that continues that pathway, and ATP would not be produced and rigor would result. There are plenty of videos of people cramping at the end of a marathon. So there is some evidence supporting this type of model, but no questions the validity of this argument because ATP levels are protected and they do not drop below 60% of resting levels. And truly, when we're at the end of a graded exercise test or an end of a marathon, the vast majority of people are not cramping and seizing at the end of the race. There's other reasons why people are slowing down and stopping exercise other than energy availability. But this is good to keep in mind. And if we look specifically at the availability of muscle glycogen, is the availability of this substrate, is this related to endurance performance? And it makes sense because glucose is needed to produce ATP, not only by the breakdown of glucose itself, but also we say carbohydrate, fats burn in the carbohydrate flame. That is, you need some carbohydrate metabolism even to use fats as a substrate. Okay, so this availability of muscle glycogen is a critical factor, but we got to try to understand it a little bit. So there is evidence supporting the idea that endurance performance is limited by muscle glycogen levels. Muscle glycogen levels, for example, were low in athletes when exercising to exhaustion at 60 to 80% VO2 max. The hypothesis being that low levels of muscle glycogen contributed to that fatigue. Athletes on a high-fat diet had lower exercise performance than those on a high carbohydrate diet. The starting level of muscle glycogen may have been lower for a low-fat diet. And if you have a starting place lower, then maybe what happens is the muscle glycogen gets depleted faster, causing the athlete to have a worsening endurance performance. Athletes who carbo-loaded outperformed those who did not. We actually saw this in the previous presentation. This is questionable in terms of what's going on with carbohydrate loading, and we've seen some data where the performance was not influenced by carbohydrate loading. But the observation being there is a linear relationship between pre-exercise muscle glycogen and duration of exercise that can be sustained. The hypothesis being that superior endurance performance resulted from higher pre-exercise muscle glycogen levels, which delayed exhaustion. That is, delayed the onset of muscle glycogen depletion. Now, I should back up and state that Noakes wrote this chapter prior to changing his mind based upon data on how to fuel for endurance events. And Noakes is very much more so presently an advocate for using more of a high-fat diet versus a low carbohydrate, or excuse me, versus a high carbohydrate diet. And so he's even stated, and I've talked with him, that if he could take this chapter out, he would like to rewrite it for everyone. But this continues to be a source of discussion amongst endurance athletes of how much carbohydrate to take in. And truthfully, I think it's probably somewhere in between the middle of being a low carbohydrate and a high carbohydrate diet in terms of performance. Here's some more data on carbohydrate muscle glycogen and endurance performance. We have initial muscle glycogen levels on the y-axis. On the x-axis is endurance time at 75% VO2 max. And we've got three groups, one on a high carbohydrate diet in the filled in circles, mixed diet in the gray circles, and low carbohydrate in the open circles. So this is endurance time at 75% VO2 max hours. And so endurance time is influenced by the levels of initial muscle glycogen in the muscle. Okay, so let me go to some highlights. Three groups trained: low carbohydrate diet, mixed diet, high carbohydrate diet. Pre-exercise levels of muscle glycogen were related to time to exhaustion at 75%. Okay, a couple things. One is I actually think he's got his circles mixed up, because if you exercise for 75%, initial muscle glycogen levels being higher would be for the high carbohydrate diet, not the low carbohydrate diet. But initial exercise muscle glycogen levels would be higher for if you're eating more carbohydrate than less carbohydrate, and they were going further. So there's this linear relationship between pre-exercise muscle glycogen and endurance time to exhaustion. Another thing that's really important to mention here is this is a protocol that's very common to use in research, but it's not a protocol that we use in real life. What this does is measure the time to exhaustion at 75%. That is, you set a bike to a resistance level, for example, that would be 75% of your VO2 max, and you keep biking until you can't bike anymore. So you go to exhaustion. You don't know when the end of the event is. In reality, what we do is we run a 5K. We know how far we need to go, or we run a 10K, or we run a marathon. We know the distance that we need to cover in order to complete the event. These protocols is very open-ended, and you need to be highly motivated as an athlete to do this type of exhaustion protocol. All right, so some highlights. The relationship between glycogen levels and performance is associational. There may be something else going on that interferes with performance. Noakes starts to raise some of these issues. It could be a placebo effect. There could be something central going on in terms of a glycostat, that if there's low levels of blood glucose, maybe the brain is actually starting to shut things down, shutting muscles down. Or maybe there's something about rising body temperature. And this is another theme that we'll get to in chapter 4 on core temperature and thermal regulation. All right, so here's some more data. Muscle glycogen on the top plot on the y-axis, respiratory exchange ratio on the middle plot, and blood glucose levels on the bottom plot. We're going to go a little bit more detail on the RER in just a bit. Well, let's look at muscle glycogen, and we've got 3 diets here, and it's hard to distinguish between these diets. This is the mixed diet here. This is exercise duration. So this would be the low carbohydrate diet, low carbohydrate. And the what's illustrated here is muscle glycogen is started low for the low carbohydrate diet group, ended low as well, mixed diet in between. And if you ate a hard carbohydrate, you had initial high muscle glycogen levels and then depleted at the end where they went longer. So again, this is evidence supporting the idea that if you maximize your muscle glycogen, you can delay the onset of fatigue, the onset of exhaustion. You can go further, you go longer at a particular intensity. Blood glucose levels, this is the transport of glucose from the liver to the muscle, is also varying based upon muscle glycogen levels. And we're going to talk more about blood glucose levels as we go along. So liver glycogen levels could, something that is important that Noakes raises is this data set does not have liver glycogen levels. And maybe liver glycogen levels could have been depleted pre-exercise for one group over the other, especially the low carbohydrate group. So maybe what's going on is the liver glycogen is depleted for the low carbohydrate group. And that's the issue that's causing exhaustion, not the depletion of muscle glycogen. It's not clear if the cause of exhaustion was depletion of muscle glycogen or liver glycogen, because liver glycogen is the repository of glycogen, and you release that glycogen into the circulatory system, and then it's blood glucose. Okay, some challenges with this idea of muscle glycogen being a root of the limit to performance. There's no direct evidence that any one phenomenon, for example, muscle glycogen depletion, causes exhaustion. The model is based on the association of muscle glycogen and exhaustion. There may be something else going on as muscle glycogen is depleted, and that something else is the reason for the limit to performance. For example, if there's reduced blood glucose concentration, the brain may actually be detecting low levels of blood glucose, which would be an indication that liver glycogen is getting depleted. The brain may detect that low level of blood glucose, and then it may automatically start reducing the amount of muscle activity. That's a central governor model. Okay, that's a glycostat. We don't know if this is true, but there's some evidence. We'll talk about this in a little bit. There is some evidence that low levels of blood glucose, independent of muscle glycogen levels, may actually be a factor for fatigue. And that makes no sense because the blood is in the, the blood glucose is in the blood, not in the muscle. So we'll go through this. And let me jump ahead a little bit because it is an interesting part. There's been some studies where people will swish and spit a glucose drink during endurance performance, and they can have a benefit to an endurance performance simply by taking the glucose drink in the mouth, swishing it around, and spitting it out. You can have an increase in performance, endurance performance. That makes no sense. But it does make sense from a central governor model that if the brain detects that, oh, well, we're going to be getting some blood glucose now or getting some glucose to the muscle, this is a good thing, I'll let you continue to exercise. That's a central governor model issue. Something else that might be going on during these research projects or these exercise to exhaustion is rising body temperature. The body, and we'll see this later on in chapter 4, the body regulates core temperature in a very narrow band. And if core temperature starts to rise due to increased muscle activity, that it may shut things down. It will tell the person to stop exercising in order to prevent any further increase in core temperature. We don't know if there's a stretch shortening cycle fatigue. This would involve reflexes in the muscle that may be regulated during endurance events, some damage to muscle. We don't know if it's a central fatigue issue or it's a peripheral fatigue, central being more related to the central governor model, peripheral fatigue being what happens at the muscle level itself. And we also don't know the influence of placebo effect. And this is really important and tough to tease out in our research is the placebo part, that if we think a high fat diet or if we think a high carbohydrate diet will improve performance, that might actually have a factor in our performance. But we do know ATP is not depleted at exhaustion, which means ATP is available, and rigor, that full contraction, is not present. The key to carbohydrate loading, and this goes back to the previous presentation, maybe the 3 days of carbohydrate depletion, and this is where Noakes brings the central governor model back in, is the depletion of carbohydrate. Is that a way to tell the central governor to accept lower levels of blood glucose concentrations? We don't know. It's an interesting question, but can you train the system to tolerate lower levels of blood glucose? Because remember, you have plenty of fat in your system, in your body, to use as fuel. So it may not be, glucose is not the end all to chemical energy in the body. Evidence is building that athletes can adapt to different diets, diet, for example, high fat diet without sacrificing endurance performance. This is more of a contemporary thinking. The hypothesis that exhaustion occurs at low muscle glycogen levels is not tenable for athletes who have adapted to a high fat diet. And this is important, is that there may be some options available for athletes, and it may be important to include fat in a diet and maybe even in a race plan. So this isn't easy to figure out, and I'm certainly not going to recommend one type of diet over another. And in fact, a lot of times what has to happen is the athlete has to figure out what will work for her or him. And so we do lots of training with different types of nutrition plans to try to figure out what will work. Having a sufficient level of muscle glycogen is important to endurance and performance. Okay, that does seem to be the case. You don't want to run this to zero. But what role is fat going to play? And can you train the system to be metabolically flexible, or metabolic flexibility to incorporate fats as a fuel? Can you become fat adapted? Is that important? Is that help with endurance and performance? Lots of questions that are still trying to be answered related to this. It's also important to recognize the mechanism of fatigue, the limits to performance. They're not known. We simply don't know. It's a very complex problem involving core temperature issue, muscle glycogen issue, placebo, psychological issues, what have you. It's not clear what role pre-exercise muscle glycogen levels play in fatigue. Low levels during exercise may trigger some other mechanism that leads to fatigue, and low levels during exercise does not always lead to fatigue. So there are some challenges here. Carbohydrate loading, when I've talked about this, I just want to be careful. We don't want to say carbohydrate loading does not work. There may be things important in carbohydrate loading that does work, but the information that we've covered should be taken to understand that the mechanism explaining the relationship between performance and carbohydrate levels is not known. And that's why a lot of our advice for endurance athletes is to have a good regular diet and to maintain that diet through race week. You don't change the diet in the days leading up to an event. You try to maintain a good diet that's going to provide the right macronutrients for you. It's not clear how placebo effect influences the studies, especially if we start using a paradigm like time to exhaustion type of studies. Does carbohydrate loading improve endurance performance by delaying the onset of liver glycogen depletion, which causes hypoglycemia, low levels of blood glucose? That's a good question. And we just don't know enough about this. But it is critical to have carbohydrate and fat availability during endurance performance. So now it's just a matter of what amount, how to take it in, how to access it, how to train the system to use carbohydrate, how to train the system to use fats. So summary of part 3, limits to performance, we talked about that. Central governor model, we continue to use this as a theme. Fuel availability, carbohydrate, muscle glycogen, liver glycogen, and blood glucose being that interplay between liver and muscle. And then we talked about energy depletion, specifically muscle glycogen depletion. Okay, thanks everybody. Let's continue this in the next presentation.